Oh, actually, this is the last lecture, okay? And next Monday, we will have a Q&A session. And there will be no attendance check next Monday. And there will be quiz 2 next Wednesday. It will cover all the materials. So before the midterm, okay? But I expect that would not be, too much difficult. Okay, so if you follow all the materials, all the content, then might be easy, maybe. Okay, and so this is the we are learning the real-time object detection pipeline, and YOLO is definitely one of the real-time pipeline. Now it was YOLO version 1. Okay. I introduced YOLO version 1, but it is now we are having YOLO version 11. Okay, and actually, YOLO version 8 maybe have the segmentation and also the post-estimation model for the human body. So, anyways, YOLO is becoming more practical nowadays. So we are now seeing how YOLO version 2 is improved compared to the YOLO version 1. So there are several schemes added to the YOLO. And the first thing was the batch normalization. So as I mentioned to you, the intermediate responses of the CNNs, that is, how to say, their scales are kind of random. So we cannot constrain their scales in the vanilla CNNs. But so for normalizing their responses, we normally do this batch normalization, and this is also effective for obtaining better YOLO model. And what we do for that is we calculate the mean and also the variance for the mini batch, their images. So normally we have 16 to 32 images in the mini batch, or that number can be varied according to your setting. And we apply the subtraction using the mean value, and also we divide it by the root mean square of the variance. Okay. So we get the normalized response. And this response is always follows the normal distribution whose mean is 0 and whose variance is 1. So the network training that becomes more stable thanks to this normalization. And another thing we have to remember is at the testing stage, we only have the one sample. So there's no other samples that we can calculate this mean and variance. So we need to learn during the training stage. We have to train 2 additional parameters that can normalize samples during the inference step. Okay, that's the batch normalization. And okay. So using the batch normalization, this is the baseline having batch normalization from the YOLO architecture, and there you can see their MAPs are improved by 2. Okay, and also the next thing is original YOLO. It is using the 448 by 448 dimensional image as the input, but their backbone network was the VGG16, okay, which is trained for image classification task and using the 224 by 224 as the input size. So YOLO version 2, they fine-tune the classification network at the resolution of 448 by 448. And then they fine-tune this network for the object detection task. Okay. So this is the figure for that. And also for using the anchor box, okay, rather than using this kind of 98, we divide the overall images into 7 by 7 grid, and we estimated 2 bounding box for each grid in YOLO version 1. But this limits the capability of YOLO in terms of the recall. So in YOLO version 2, we try to secure more bounding boxes from one image. So in that purpose, we use some scheme called as anchor boxes. And for that, we actually do this. So anchor boxes that is obtained actually, so this is the 2D feature map we will get from the original image. Rather than using the grid, we directly apply some CNN operations, and then we obtain this kind of intermediate 2D feature map whose dimension is 32 by 32 in this case. Okay. So, and also you have to notice that when using the anchor box scheme, sorry, I already mentioned you that we use the 448 by 448 images before, but I mean, they're using this CNN operation, we normally, reduce the image size, image dimension by 32 times. So when we input 460 by 416, 416 by 416 images into these CNNs, then we reduce their dimension by 32 times. So we can, we can result in this 13 by 13 dimensional 2D feature map, okay? But if we input 448 by 448 image, we may have 14 by 14 images that feature maps in the middle, okay? Are you guys following this? Okay. So, but, this can also be good, but the authors are saying that they want to locate the center. Maybe this is not a center. I don't know. But if the width and height of the 2D feature map, if that is the odd number, then we can define the center position, okay? Then at the center feature map, there would be just 1 by 1 pixels there. But if we have even numbered width and height, for example, 14 by 14, there would be no center, but in the center, there would be 4 pixels. Are you guys following this? So the authors are saying that they prefer to make the width and height in the odd number. So they on purpose reduce the size of the input image into 416 by 416 instead of the 448. Okay. And anyways, they instead of making the grid, they directly get this 2D feature map, and then for each feature map cells, they estimate several bounding boxes, which is called as the anchor box. Okay, so in that way, if we estimate 5 bound anchor boxes for each 2D feature pixels, then there would be 13 by 13 by 13 times, and 5. Okay, totally there would be 445 bounding boxes will be estimated from this 2D feature map. Okay, so this is the scheme called as the anchor box. Okay, previously we divide the image into the grid and then estimate the 2 bounding boxes for each grid, but instead we get the 2D feature map now and estimate more bounding boxes for each feature pixels. Okay, that is also called as the anchor box. Okay, So if you use anchor box scheme, as I told you, the MAP, which is the precision, could be slightly reduced. Okay, but so the MAP become less because you predict 10 times more bounding boxes. Okay, because of that, your prediction could be wrong sometimes. So because of that, the MAP could be less, but it raises the recall from 81% to 88%. Okay, so it can more accurately cover the ground truth in the images. Okay, that's the anchor box. And actually, the 5 bounding boxes here, this type of bounding boxes are hand engineered. Okay. Actually, this scheme, the anchor box scheme, was used in other object detection algorithms, but YOLO haven't. So the author tried to involve that scheme, but previous method usually involve this type of hand-engineered bounding boxes, 5 bounding boxes, but they are hand-tuned. Okay. But what they are saying here is they apply the k-means clustering, which is the clustering algorithm. So you can get some bounding boxes from the training data, okay? And you can actually cluster those bounding boxes. So you want to find some bounding boxes which might be frequently observed for the your training image. Okay, so that is done by this k-means clustering algorithm. So these anchor boxes is need not be perfect because we will adjust these anchor boxes later step. But if you have good prior for these anchor boxes, then that will also raise your performance. So they want to get good priors for the bounding box shapes by applying k-means clustering on the training set their bounding boxes. Okay, so anyways, this is if the training data that is small in scale, then that it could be thought as the overfitting. But you can see here here this is visualizing 5 bounding boxes found by k-means clustering, and this purple box is showing the bounding box for I think that's the VOC. Purple is for VOC. This is VOC, and this bounding box having no color, or the gray color might be the bounding box obtained from the COCO dataset. So you can see those 2 bounding box sets are relatively similar. So this is also showing that there is no overfitting to one data set. Okay, so this is the center pixel, and rather than estimating using this kind of hand-engineered bounding box, okay, you will use this type of trained, k-means using the k-means clustering, you can find some optimal bounding box sets for the training data. So this is that, and you will use this as the initial bounding box. Okay, their anchor box shapes. You will use this. Okay, and also because they are using 5 anchor boxes, because that trade-off, there's some trade-off between the number of bounding box and the speed and accuracy. So there's trade-off between accuracy and speed according to the number of bounding boxes. But they are saying, the authors are saying, the K is equal to 5 if they use 5 anchor boxes per each feature pixels, then that best trade-off between the speed and accuracy. So because of that, they use 5 as the anchor box number. And also previous in YOLO version 1, they directly estimate the XYHW, which is the center position of the bounding box. Okay, this is the center position of the bounding box and width and height of the bounding box directly from the CNNs. So you have to estimate their, absolute value directly. But in YOLO version 2, rather than directly estimate their values, you will instead estimate this Tx, Ty, Tw, and Th, and To. To is same as before. This is the confidence value, okay, which multiplies the objectness with the IOU between the ground truth box and the predicted box. Okay, this is confidence value, same as before, but their width and height and center positions are now obtained offset to the anchor box location and their width and height. So we detect the optimal set of the anchor boxes in the previous step. And this PWPH is the anchor boxes, the prior width and height. And we only estimate this TW and TH, which can adjust the prior information's their ratio. Okay, so I mean we can reuse PW, but we can adjust their scales only. So this is more accurate and more easier to be trained. So YOLO version 2 are using this kind of scheme. And also the CXCY, that is meaning the position of these feature pixels, okay? And they only estimate their relative positions. Their, in this cell, they can estimate their, this is sector sigma ty, and this is the sigma tx. So they only estimate the offset from their this left top positions. Okay. So this is we are calling that this is we only estimate their offsets and scales. Okay. This is easier to estimate rather compared to estimating the low values. Okay. Are you guys following this? Okay. So this PWPH, this is the anchor box prior we obtain. We will use 5 anchor boxes per each pixel. And there are some templates, and we only adjust their scales and their offsets. Okay. And this scheme actually improves the performance a lot. So if you use dimension prior, and also the location prior, the MAP, that will, greatly improved. Okay. So this is the 2 important schemes as well. And also they apply the multi-scale training. And this is not also very difficult to understand. So original YOLO uses the input resolution of 448 by 448. And YOLO version 2 with anchor box scheme is using the input image with this dimension because they try to secure the intermediate features to be odd, to have the odd height and odd width. Okay. But they use this as the main input feature, a main input dimension. But instead of fixing the input image size, they try to involve multiple input image sizes. So, but they try to make it, make the offsets to be 32. So, and here's 448 and 418, maybe 80, and so their offset is 32 always. Okay, because they reduced their feature 2D feature map that will be that will have how to say the 1 pixel more in their feature map if they offset their input size by 32 pixels. Okay, so that is the 32 coming from, and I mean, so they adjust this to be multiple scales, and they actually train the YOLO version 2 using these multi-scale input images. Okay, so for every 10 batches, they change their network input size and train the YOLO version 2 model. And this multi-scale training, this is very simple, but it can actually improve the accuracy by 1 MAP. Okay, and also they involve the new network, which is called as the darknet. Okay, so previously they used VGG16 architecture as their backbone network. Okay, but they somehow adjust. Okay, and actually they tune their network to have 3230 filter in their convolutional layers. And also they double the channels after the pooling step. So using this design choice, they make another network called as the darknet 19. And they are saying that this is faster than VGG16 and more stable for the object detection task. Okay. And they are called as darknet 19 because they have the 19 layers. Okay. So using this new network, their MAPs, new network, yeah, MAPs are slightly improved. You can see here, 0.4 MAPs are improved. Okay. And also they do multi-scale training. So, I mean, this is similar to what I mentioned here. This is the multi-scale training, but what I mean is this is a higher resolution image scheme. This is similar to multi-scale training, but they actually chose their final network, their input size as the 544 by 544 rather than this. And they find that their MAPs are becoming also improved. So in the final model, they are using these 544 by 544 images. Okay. So when you use this high resolution detector, then our MAPs are also 2 MAPs are further improved. Okay, so I already explained all of them: batch normalization, high resolution classifier, and convolutional. We remove the pooling and FC layers, and instead we involve more convolutional layers, and we use anchor boxes, new network, which is called as the darknet, and dimension prior and location prediction for using the anchor boxes. And also I missed one thing, pass-through network, and we do some multi-scale and high resolution detection by increasing the input image size or varying the input image size during the training. We can improve the performance. And actually, there's one more thing, pass-through layer. This is also very simple. So what they motivated was to develop this layer is, you can see this part. So here, this is the intermediate feature I mentioned. This is 13 by 13 by 412 dimensional array. And from here, you apply several CNN network again and get this dimensional response, okay, originally. Okay, and you can apply here the anchor boxes and estimate the bounding boxes, okay? But here, when using this pass-through layer, you will have one another, flow of the signals here. So what here they do is, in here their dimension is 26 by 26 by 256, okay? So their 2D dimension is twice than the later feature, okay? Are you guys noticing this? So the subsequent features are, their dimension is two times reduced, and having 13 by 13 dimensional image. But in previous layer, they are having 26 by 26 dimensional image here, okay? And they are saying that they can want to involve, when doing the final estimation for the bounding boxes and classes, they want to involve higher resolution features as well, okay, combined with the low resolution features. So they try to involve one another flow of the signals here, and they actually reshape this dimensional signal into 13 by 13 by 2048 dimensional signal, and then concatenate these two to make 13 by 13 by 3072 dimensional features. And then they estimate their final bounding boxes and classes using this feature. Okay, are you guys following this? Okay. So having one more path to combine the higher resolution feature and low resolution feature, that is the pass-through layer. Okay, and using this, there was 1%, actually 1% gain in MAP. So this is the published paper, but most of the contributions are not that major, not that significant. Okay, but they are that how to say, the small contributions are combined to make the YOLO version 1 to have this amount of performance improvement. Okay, that's the YOLO version 2. And actually, this reported baseline is not using anchor boxes because it is because if they use anchor boxes, then MAPs are also slightly reduced, but instead the record is slightly improved. So they didn't actually report the YOLO version 2 with the full schemes, but later versions are using the anchor boxes. Okay. And actually their final model is also using the anchor boxes. And this is the YOLO version 3. Okay. So, and this is not the published paper, but this is the technical report, but authored by the main author of the YOLO version 1. But later versions, it is not maintained by the author of the YOLO version 1. And here, what they are saying is, this is now the time, not FPS. Time is similar to 1 over FPS. Okay, so time, it is smaller is better. Okay, so YOLO version 3 is here. Compared to others, it is very fast actually. And this is the precision. Okay, and precision is comparable to the state of the art. That's what they are saying here. And there are very small improvements, but most important thing is they actually consider more multi-scale needs in object detection task. Actually, another important weaknesses in YOLO version, previous versions are they cannot predict small objects properly. Okay, they cannot properly deal with the small object. And to improve this aspect, what they do is maybe here there's more figure. And similar to previous, this n is now saying the dimension of the 2D feature map. Dimension. Previously, it was 13 by 13 in YOLO version 2. And we estimated 5 bounding boxes before, but here we will estimate three bounding boxes for each pixels in the 2D feature map. And that will actually have this dimensional information. So 5, that is the width, height, and center, x and y, and confidence. So that's the 5-dimensional vector here. And 80, that's the class, number of class. So previously in YOLO version 1, there was only 20 class, but YOLO version 3, they are having 18 because they are using different data set. So almost same, this part is almost same as before, okay? But different thing is they will estimate this for 3 different scales, okay? So this is defined for 3 different scales, okay? That is the important difference to previous version. And this is somewhat complicated, but what they do is actually, this is the input RGB image. And this is some convolutional layers. This is some convolutional layers, and this is the residual connection we learned for from the ResNet. That's the similar thing. And then what they do is they actually this is also the further streams of this CNN network, and they actually estimate 3 feature map differently to previous. They actually estimate 3 intermediate feature. The first feature is 13 by 13 dimension, and the next is 26 by 26 dimension, and next is 52 by 52. So this is same as before, but we have more finer grained feature map now. And when calculating that, we also use some previous layers response. We concatenate them when estimating this final scaled feature map. Okay, are you guys following this? This is not that difficult, right? This is more like the engineering thing, right? And then they infer this dimensional information for 3 different scales. Okay, so previously n by n, this is 13 by 13 by 3 by 85, and here we infer this dimensional information, and here we infer this dimensional information. Okay, so all are the bounding boxes estimated. Okay, and we have many bounding boxes from one image. Okay, and also because thanks to this, the YOLO version 3 is becoming too well capturing the small object. So this is relatively limited for capturing the small object, but these feature maps are having the finer grained feature map, so they can better capture the small object. Okay. And another thing which is improved compared to the YOLO version 2 is they proposed the darknet 53 architecture compared to which is more powerful than the darknet 19 they proposed in YOLO version 2. And the main difference is they use the residual connection, similar to ResNet. Okay, at this time, as far as I remember, the paper was published in 2017. At that time, ResNet was the state-of-the-art CNN architecture. So they make their own darknet resembling this ResNet architecture, having the residual connection. And also they make the architecture deepen compared to this 19, darknet 19 that have only 19 layers. They make this darknet 53 having the 53 layers, which is more deeper than previous version. And at the same time, they involve the residual connection in between the convolutional layers to prevent the, that vanishing gradient effect, okay? And you can see here, they are insisting that darknet 53, that's slower than darknet 19, right? So this is previous YOLO version 2's main architecture, and this is the YOLO version 3's main architecture. So FPS, the larger is more faster, okay? So YOLO version 2, their backbone is the fastest architecture. But YOLO version 3, they are using darknet 53, which is deeper than 19. So, FPS is less competitive, but still they are better than ResNet architecture, which are the state of the art. And at the same time, compared to YOLO version 2, their accuracy is greatly improved and almost comparable to that of the ResNet. Okay? And in other words, the darknet 53 is their performance is comparable to ResNet, but their speed is faster than ResNet. Okay. So that's the reason why the authors are using this darknet 53. Okay, so this is actually the main thing proposed in YOLO version 3. So they actually use the multi-scale encoder. Okay, the multi-scale, they obtain the multi-scale feature from the images to better capture the small object. And also they make the backbone deeper than before to secure the better accuracy and also retaining the real-time needs. Okay. In summary, this is the YOLO version 3. Okay, are you guys following this? Okay. And actually, this paper is published early this year in CVPR, which is the top conference. And previously, this YOLO was the only real-time pipeline for object detection task, which also secured the good performance. But DETR is definitely one of the state-of-the-art object detection pipeline. And now the paper is saying that now DETRs are beating YOLO on real-time object detection task. Okay, and this is authored by Baidu, China. Okay, and this is their performance. So, this is the accuracy, and this is the time. So, if you go here in this direction, it means the faster, and if you go this direction, it means the algorithm is more accurate. So their algorithm is located here, both fast and more accurate compared to the YOLO version 8. Okay. Actually, most of the features are similar. YOLO version 8. Most of the features are similar to YOLO version 11. So, the accuracy. You can regard this as the state of the art, actually. And that is actually located here. Okay. And the DETR, we already learned about the DETR, and this RT is meaning real-time DETR. Okay, so DETR is actually very slow because if we have n input, their attention mechanism, their time complexity is order n square. And also, many researchers have found that, transformers, their architecture is composed of the encoder and decoder, but especially encoder that accounts for most of, or almost half of the overall complexity, okay? Overall time complexity encoder accounts for, but they contribute only 11% of the accuracy in previous DTR algorithms, okay? So they are pointing out that their encoder could be more, efficient, okay? And also they say, as we see in YOLO version 3, this type of multi-scale feature that can be helpful to capture multi-scaled object, okay? So actually this multi-scale feature that is helpful for improving the performance of the object detector, but at the same time, it can reduce the time, reduce the speed of the algorithm because we extract 3 times more features compared to the single scale algorithms. The processing time could be become triple compared to the single scale algorithm if we use the multi-scale algorithm, right? So this is the 2 challenges when motivating this real-time DTR. So this is the pipeline of the RT-DTR. Okay, so they are very similar to what we have learned. So this is the original image, and they first extract the feature from the backbone, and then they apply the encoder and decoder of the transformer to output both the bounding box and also the class probability for each bounding box. But especially they propose some schemes in encoder side first, and they actually propose this AIFI, which is the intra-scale feature interaction module, and CCFM, which is the cross-scale feature fusion models. Okay, and they actually extract 3 scale feature. Okay, from the image, they actually extract 3 scale feature, and each feature, if they are extracting SI feature, then their feature dimension becomes like this. So if they extract S3, then their width and height becomes 8 times reduced. And if we extract S4 feature, then their width and height, that will be 16 times reduced, okay? And S5 feature, that will be 32 times reduced, okay, compared to the original image. So this is the smallest, but having the higher resolution, more semantical information. And also this is the widest, the S3 is the widest feature map, having some detailed information about the images. Okay. So actually they extract 3 different scaled feature map. And if we encode this using the transformer encoder directly, then the time complexity might become 3 times or 2 to 3 times compared to the single scale transformer encoder. So are you guys following this? Okay? Because we are using multi-scale feature, the time complexity might become heavier than before. And also, the attention mechanism, their time complexity is order n scale. So if we use three times more information, then the time complexity might be exponentially increased. Okay, so their idea is this. So they only use S5 feature, which is the smallest, for the transformer encoder. Okay, that is actually the intra-scale feature interaction module, which is actually the single layer of the transformer encoder. Then they will first improve the feature here. So previously it was S5, but we will denote it as the F5 because it is one time improved by the transformer encoder. And the remaining more larger scale feature, we will combine it later using the fusion network, which is composed of the convolutional, mainly the convolutional operation. So we combine this F5 with S4 to make this, and also apply these two fuse with the S3, and use, output this in here, and also input this, and combine this intermediate information to make this output, and also use this intermediate output with this signal. Then we make the output again here, and we concatenate all the responses here and use it as the encoder's output. Because this part is mainly composed of the CNN architecture, anymore we don't need this n-scale time complexity modules. Okay, their main idea is they apply only the smallest feature map for the transformer encoder, which is inefficient, and remaining features we will combine that using the CNN modules. Okay, so that is the main idea, and that is called as efficient hybrid encoder. Hybrid, we call this as the hybrid because we combine the transformer encoder and also the CNN. Okay, so that in that sense is the hybrid. And previously, the two problems are now solved. Multi-scale features we have to involve for good accuracy, but it hinders the real-time speed. So rather than using all scales into transformer input, we use only the smallest feature map and combine it later with the CNNs. Okay, and also the encoder, their time complexity is very inefficient, but their accuracy contribution is actually less compared to the decoder. So by proposing this kind of module, they can solve those problems. And another important contribution of theirs is the query selection, IOU aware query selection method. This is actually hard for you maybe to understand properly, but actually there are query selection method in, this is not proposed in original DETR, so you don't have to worry too much. But query selection is, what they do basically is, query is the input to the decoder, object query. Maybe you remember that. Object query, that's the input to the decoder. And also the computational cost of the transformer decoder also depend on the number of object queries. So if you select the top best, top queries which produces good accuracy among the all object queries, then that will increase the speed, and at the same time that will also helpful for securing good accuracy. So they actually do query selection, but using this additional IOUs. But I personally think this is not that important scheme. So you don't have to understand at this time. But if you are interested in, you can refer this paper and their code actually. And actually, this is the RTDTR. They optimize the encoder side rather than using the the original encoder of the transformer. They can improve their speed and at the same time the accuracy. So now the RTDTR is the state-of-the-art real-time object detection pipeline. And actually, this is the RTDTR. Okay, they have several models using different backbone algorithms. And this is the YOLO algorithms, and this is the DTR variant. So this is the original DTR, and there are many variants in DTR, but actually this Dino is the state-of-the-art among the DTR variant. So you can refer actually the Dino pipeline, their paper, for if you are interested in. And you can see their AP is actually RTDTR. They are beating the best YOLO version. Okay, and also it is better than also the best DTR variant. And this is the speed comparison. This is the real-time pipeline. If an algorithm is having the FPS larger than 30, that is called as the real-time algorithm. So most of the YOLO variant, they are having the FPS larger than 30. And also RTDTR, it is also having the larger values and even larger than the YOLO. Okay. Though they are using the DTR, the transformer-based operation, they can be tuned to be faster than YOLO. Okay, and DTRs they normally don't report the FPS, but the Dino it have 5 FPS, which clearly shows that their algorithm is not real time, and their performance is limited. Okay, to around 50, but RTDTR, their performance is almost close to the 55. Okay, so it's good. And this is, this is the final AP, and this is AP for some of the subsets. Okay. So this is the RTDTR, and this is all for this class. Okay. Anyways, thank you for listening this class, and let's see next Monday for the Q&A session. Okay, thank you.